All right. Good morning. This is the last lecture, and we'll continue the review. I wanted to say that these reviews are a little, I mean, obviously I'm not covering everything. It seems a little random which problems I pick. If you have feedback, please let me know. I think I do mostly routine problems here. Maybe some of you want to see crazy difficult problems, but if you think about it, the midterm, the way I see it, the midterm was mostly routine problems. But maybe you don't agree. But when I say routine problems, I mean things that are not that different from the earlier, from the first half of the homeworks that are assigned in each section. At the end of each section, sometimes there were these more difficult things. You have to unnest some Runge-Kutta or show something using some mean value theorem and stuff like that. We didn't have too many of those on the midterm. But, so I'm picking more or less routine problem. I'm giving you some intuition. I think a big difficulty for some of you is to figure out what to do on the routine problem. So for example, on the midterm, I have this parametric curve. I think many of you went in the wrong direction. It was really just a polynomial fitting. So giving you a big picture, I think, is the thing to do. Regarding practice, as I said before, go through the old midterms that we posted. I will go through the ones that I have not posted but are on the exam archive and just tell you which problems you can do. But in short, you can do almost everything. This course has been taught very similarly since the 90s. So most of the problems you'll be able to do. And I think you'll get a good feeling for it, for which problems are good. And then next week, I'll have office hours. Just come to me in GSIs and ask if you get stuck. There are not solutions to all of those. In fact, some of the ones I posted don't have solutions. Come and ask. First, try to convince yourself that you're correct. You'll learn a lot by figuring out. If you derive some coefficients for some quadrature scheme, you can test it. Just plug in. I mean, you can't be sure that you're right, but you can at least convince yourself you didn't mess up completely. That gives a lot of understanding. Don't forget to go through the homework and the programming assignments. I thought today also we could just go through and as I go through the earlier material, just reminding you guys about some of the MATLAB codes that we have. And they really do give a lot of understanding. And they are covered. I might very well ask something involving the MATLAB codes or coding. And you know, you've done 4 programming assignments, and it's a huge part of the course. So hopefully we'll be able to do that. I'll just start. I didn't quite finish up the, let me just remind you, since it is such an important part of differential equations. Last time I did this, I took a scheme that looked like this, and I asked, what is, and this is, as I said, routine problem in the sense that, you know, it's pretty straightforward what to do. We derived a tau. So the question is typically, is this method convergent? Okay? The question might also be, what is the order of convergence? But what you do is, of course, that you identify that it's a multi-step method. You go right to, you recall the fact that a multi-step method has 2 parts of showing convergence. Namely, you need to show consistency and stability, right? And consistency is really just showing tau. So the first thing we did was that we found a tau. And after a lot of work, that ended up being what? Order h squared. All right? How did we do that? Tailor everything. Or not everything. Tailor the things that need to be tailored, namely I plus 1, I minus 1, I minus 1. Okay? This one we could leave. First of all, of course, you need to know your definition of tau, which is just plug in y instead of w's, basically. You tailor everything, and you get this out when you're said and done. And that's kind of good, but you're not done yet. And the things I had to rush last time is that in order to show that a multi-step method is convergent, you need to show stability as well. And stability that we do by doing the root condition. So so that's, you know, it is straightforward, but you need to do it. Condition. You form this polynomial p of lambda. You look at these numbers here. Remember, this stability concept does not involve the f at all. It looks at these 3 numbers here, moving them over to the left. It's a 2-step method, so the highest power is going to be 2. That's easy to remember because this is kind of the lowest one. So if this is 1, this becomes lambda, this becomes lambda squared. So it's pretty clear this is going to be a lambda squared and then a minus, I forgot something, a 4. Minus 4 lambda plus 3, right? That's the characteristic polynomial for this. And the root condition, these have these lambdas. And the root condition is very simple. Basically, they have to be less than or equal to 1. But if they are 1, they cannot be repeated. Okay? And in this case, it's not even an issue because it's just not satisfied. The 3 is blowing everything up. So this means that it's unstable. It's not satisfying the root condition. And that in terms means that there is no convergence. And I did mention that if the only question on this problem was, is it convergent, you might want to determine that quicker and save yourself 10 minutes of work here, right? But likely, I think I would like to see, probably many of these problems, we would like to see you doing this. So we would say find tau, and then is it convergent? You'll see when you do the old exams how it's, I'm just saying that, this certainly shows that this doesn't matter at all, because it's just not a working method. So someone asked in office hours yesterday, how about one-step method? There is this big messy slide of one-step method. We kind of did everything here, except maybe this part you can skip. But let me summarize it in a different way. It's still the same thing. So how it's often formulated, this condition, is that consistency plus stability is equivalent to convergence. Okay, this is the ultimate everything, in the sense that this shows that your method will give you the right answer if h is small enough. Okay? This is really just tau going to 0. This is just a local one-step error. How big is the error you make in one step, right? That's not enough in general, because you need to have this stability. So if I need to write something here, you could say that the error goes to 0, as h goes to 0, right? Stability I don't have a short term for, but without stability, you cannot have convergence, okay? And how does one-step methods fit into this? It's identical. It's just that one-step methods are always stable, okay? And that's what this slide is saying. If you have a one-step method, the method is stable, which leads to number 2, that consistency is equivalent to convergence. All right? And this short trick here of finding consistency we didn't use. We find tau, right? But it all fits the same pattern. If you want to see that one-step method, I think we did it back this. If you form the root condition for a one-step method, you'll see that it's really just wi plus 1 equals wi plus stuff involving f, right? I mean, that's what a one-step method is. So the root condition is really just lambda minus 1, which has one root at 1, and it is stable, right? So if you accidentally forget this theorem and you think it's a multi-step and you go at this, you would actually do the stability and you would find that, yes, it is stable. But it's actually, for all these Runge-Kuttas and everything, as soon as it is a one-step method, what was maybe not so obvious is that it can be written as some phi here. But it's really just a one-step method. It looks at wi and other stuff, and it takes a step, right? So if you're asked for the same question like this, and it's a one-step method, the whole problem is reduced to finding tau, basically. And that gives convergence. In this case, we have an error estimate. It's identical to Euler, just replacing the tau. Back in the Euler, when we did that, this tau here was m halves times h. Okay? And for another method, you'd have to replace it by tau, hopefully higher order of h, because Euler is just linear in h, right? Also, this L is, of course, the L of this phi here. And we did some simple case, I think, of the midpoint method. But that's how they all fit together. Kind of tricky. You'll see, I think Strain's exam has, we always like to come up with funny schemes and see what you can do about them. I mean, the whole goal of designing schemes, this was a bad scheme, so you never learned about this scheme. But the way we make them up is, of course, by just choosing these numbers, 4 minus 3, to make this small, for example. And then we might choose them such that these have roots inside 1, or not. In this case, not, right? It's just, this is how people design schemes. There are some nice theorems that we're not covering that really show what you can and cannot do. So people really struggle a lot. What is the best possible scheme? Someone asked yesterday, how could, I think, did Mingu? No, Strain. Someone had an exam with a problem where they put some numbers here and ask you to identify it. So that would also be something you see a lot in the old exam. Suppose I put an A here and a B there, and why not a C here, right? I could put stuff everywhere. And I could ask you, make a method, choose A, B, C such that this is a second order accurate convergent method. What would you have to do? Well, you would have to do everything we did here, except that every time there's a 4 and minus 3, there are going to be A's and B's, right? And it actually ends up being a linear system that you have to choose A, B, C, so you kill off terms. And then at the end, of course, this may or may not work out. So So you'll might find some of those problems. And that's how you can design schemes. We didn't do it that much. If you think about how we presented like the Adams-Bashforth, it was a completely different technique, namely integrating some approximating polynomial. There are many ways to find methods, but one is to just plug in numbers. So that's how we find all these methods. Just a few words on 511. What is a routine? I mean, it's a little abstract, and it's the last part of the differential equation. But it was a huge portion of programming assignment 4. I don't know. I mean, problem number 3, the last problem of programming assignment 4, was meant to just practice this over and over. You have one method called Runge-Kutta 4 that had a stability region, this region that is described here, which says where is this amplification factor Q less than or equal to 1. And then we drew it on the computer. It's not for program assignment 4. All you needed to know was that it was crossing here at some point. But actually, if you do remember when we plotted it, it actually looked like this. Doesn't really matter the exact shape. The point is that there was a region crossing the x-axis at minus 2.78, inside which, remember, this is a complex plane of h lambda for the model problem. Imaginary h lambda, real h lambda, right? So what this is saying is that if you want a method to be stable, you better choose h small enough so you're inside this. So a routine problem would be like problem 3a on the programming assignment. Namely, here's a method. In that case, it was actually nonlinear, but we told you what lambda was. So suppose I tell you that here's an equation, minus 1,000 y. And you want to solve this using RK4. What is the largest h you can choose? You know, clearly, lambda is minus 1,000. You're just going to choose it, so it ends up here. What if it's forward Euler? Well, then, same concept. It's just that then the region looked like this. We did this, right? So it's just a slightly different number there, not too big difference. What if it's 1,000i? Well, then clearly you would have to bring it down here, right? So you would have to know that number. That's the number I accidentally wrote in the first version of the programming assignment. But anyway, that's a number, right? You have to bring it down. What if it's 1,000i and it's forward Euler? So that's a little tricky question. So forward Euler had a stability region that was a circle, and we derived that easily. So you're basically saying that h lambda must be inside this, otherwise it's going to blow up. And I'm telling you that I want to solve an equation y prime equals minus 1,000 times the imaginary unit I times y. So lambda is minus 1,000 I, or plus 1,000. I don't care. But it's down here. What's the smallest a? How small must h be in order to be stable? 0, right? It doesn't work. You can never bring it inside the circle. So this is the way you see that forward Euler is just a bad method for oscillating problems. For the pendulum, forward Euler would be a disaster. Runge-Kutta is not such a big deal. Then in program assignment 4, we went on to backward Euler. And I know you thought it was a trick question, problem 3c, but basically, what about backward Euler, right? And then for backward Euler, so this was RK4, except for that one, right? This was forward Euler. And backward Euler had this region that it was stable everywhere, except for this little circle. And by the way, astability is an obvious thing. When you have this, you just astability means that it's stable everywhere on the left-hand plane. Okay? So what's the same answer to this question? Let's go back to this problem. So lambda is minus 1,000 over here. How small h must you multiply in order to be stable? And the answer is you can do whatever you want, right? But of course, in that problem, in problem 3c, you need to go from 0 to 2,000. So you need to take one step, right? But there is no h limitation for stability. Take whatever step size you want. How about the I one? If I have an eigenvalue down here, is there an h I can multiply by so that it doesn't blow up? Well, anything, right? Everything is covered. So that's super stable method. Yeah?
Does astability include the axis, the imaginary axis?
Yeah. There are methods, actually very commonly used methods, that have stability regions that are stable exactly up to and including that. But yeah, I don't know here, interesting. Yeah, so I know that it does, because there are methods that people use and they are astable. If you look at this definition, it doesn't quite seem to do, because they have a strict less than 1, right? Which means that if I gave you a method that was equal to 1 along here, there are a lot of popular methods that are that. That would not be included. However, they would still call it astable because astability is based on that. So I guess it would be stable for less than that. So I guess maybe this definition makes sense. But usually it's here's what I'm going to say. Depending on how you define, if you have strictly less than or equal to in your definition of the stability region, then you need to exclude it in your definition of astability. So as long as it's consistent, like up here, it's going to be fine, right? I never made a big deal about these borderline cases. Because the methods we look at were not like that. Didn't you look at, maybe you did look at the implicit trapezoid. Maybe it was an example in the book or something of a method that had a Q. Let's look at that. What is, here's a method. Equals Wi plus, how does this method work? H half of fi plus 1 plus fi. I think that's a good method. It's called the implicit trapezoidal method. And it's almost like backward Euler, except that they add this guy and divide by 2 there. Okay? And the reason it's called a trapezoid is that this is really the good old quadrature trapezoid method applied on the 2 points. But it's, of course, implicit, just like backward Euler because of that guy, right? So to find stability region of this, first you find this Q H lambda, and you do it by just looking at the model problem, always. So then y prime equals f equals lambda y, right? And you just plug it in. And what's going to happen is that you're getting y all right, what are we going to get here? We're going to get yi plus 1. We can do w's. Wi plus 1 equals Wi plus h half times, and the f is very simple. It's going to be lambda Wi plus 1 plus lambda Wi, right? And in order to solve just like backward Euler, you have to bring it over to the left. So you're getting Wi plus 1 multiplied by 1 minus h lambda half equals, and then on the right you get 1 plus h lambda half multiplying Wi. And then you divide them and you're done. So basically, one more line here would be to just say that Wi plus 1 equals, and you have the ratio here, 1 plus h lambda half, 1 minus h lambda half. Okay, and this is Q of h. I don't know if you did this method or it was in the book or something, but it's a method. The reason I'm showing it is that it's really one of these borderline type cases where you can convince yourself by just looking at this number a little bit that if h lambda has a negative real part, it's going to be stable. It's going to be, this number here is going to be less than 1. You can start off by just looking at real numbers. If you're confused by the whole complex arithmetic thing here, just look at the real numbers first. Then it's pretty clear that if h lambda is negative, 1 minus that is going to be a larger number than 1 plus that. So this is less than 1. While, of course, the other way around if it's positive. So then so it really shows that the stability region of this guy is going to be the left here. And going back to the question of whether we're including the imaginary axis or not, it depends on what you want to define. But it's an astable method for sure. Because if you do include the imaginary axis in your definition of this region, so this is included, well, then you can include it in astability as well, and it's astable. But let's not worry about that. Let's just say it's stable everywhere on the left hand, therefore it's astable. Anyway, so that's another type of problem, finding these Qs. Remember, for multi-step methods, those Qs are really difficult. Actually, I don't think you had a homework problem on it, really, because you have to solve all these polynomials to find it. It's very difficult to see this. We knew how to do it. Namely, we just take the test problem and plug into the multi-step method. It just ends up being another characteristic polynomial you have to find roots of. So we know how to do it. It's just very difficult to do a nice little Q like this and draw these regions. You can do it in the computer. But so usually this is easier done by one-step methods. All right? Other differential equations questions. It's a big landscape of methods and tricky things. It's very important, though. Do you want to talk a little bit chapter 6, since that's new as well? I said, I mean, it is totally covered, and it's a lot of linear algebra. I I don't know. I know some of you think it's so boring that I'm reviewing determinants. Others might actually need it. It's covered, okay? But I'm going to focus on what's kind of new from 54 and 110. And as I mentioned, Gaussian elimination, you certainly expected to know. Yeah? Oh, local array. OK, good. Let's stay on differential array. I like that. Local. What do you mean? The definition of it, or what typical problems to get? Yeah. So this was one typical problem, right? Where here's a method: find the local truncation error. I know Mingu is asking questions. I saw we looked yesterday. He's asking define local truncation error. I mean, those questions are allowed just because you don't have a cheat sheet. Some people ask, why can't we have a cheat sheet? Well, I think it's in your advantage not to, because then I can't ask those silly questions. I mean, but it doesn't really matter, right? But most of the questions are trying understanding. But the first thing is, of course, to know what is local truncation error. And that is defined twice, actually. I don't really think it needs to be defined twice. But they actually do it once for one-step methods and once for multi-step. So this definition is what it is. You can write it in two different forms. I kind of like the left-hand form. It's really, there are so many ways to see it. I always say plug in y in this here and divide by h and move everything to one side. That works for everything, right? And you can see that's what's going on here. If you have a one-step method, you plug in y, you move everything to the left and divide by h. You get this expression here. Another way to see it is plug in the true solution y and look at what the method would do, yi plus h phi, right? That's this one-step method. And look at the error from the true solution divided by h. If you want to do the simplification and prefer to remember that, that's fine. So the definition is one thing. But the typical problem, of course, as you've gone past that point, is usually an annoying exercise in Taylor expansions. Because just writing this down doesn't give much insight. At the end of the day, we want to see, is it small? And how does it scale with h? And that's Taylor. Multi-step method this definition is repeated for multi-step methods. And I would say it fits exactly the same pattern. Namely, if you look at the, well, here they did divide by h in these terms here. But they really did yi plus 1 minus the entire scheme divided by h. But then it turns out that these h's here cancel out, so they could write it in different form. Same thing. So that's what we did here. And again, it's just Taylor. I think that's it. Remember the definition, know how to do all this. But it's certainly routine. It is certainly an important part that shows up almost all the time, right? So knowing how to do this is just the analysis of differential equation. But then, of course, follow-up questions would be, is it convergent? And it's just quite easy, right? It's just a question of, you showed consistency by showing that I mean, if you show that tau is equal to 1 plus h, that's a horrible method. It's just not anything good about that method, right? Because you're taking a step and you're making an error that is 1, regardless of how small. How could you possibly take 1,000 step and expect to get the true answer? It has to be h something, right? So consistency is tau goes to 0 as h goes to 0. But you're not done. You need to look at stability. But is it a one-step method? Then you can just immediately say, fine, it's convergent. And in fact, order of convergence is defined to be the power. Where did that define? I think at least for the one-step method, here, we defined that, well, maybe we never exactly defined what the order is. It might be somewhere. But if you get a truncation error of order h, then we say it's a first-order accurate method. Order h squared is a second order, et cetera, right? So that could be a follow-up question. What is the order of this method? All right, yeah, that's kind of it. Local truncation error. Tau. More differential equation things? Or do you want to know linear algebra? Do you guys feel that linear algebra was much easier? Or, I mean, I'm sure there were some difficult problems. But I'm assuming you guys found chapter 6 a little easier. But I might be wrong. Yeah?
How does Taylor expansion
In two variables? Yeah. We only did this. So let's see. Everything we're doing is 1D, right? It's ordinary differential equations. So we really just have a time. We're not solving partial differential equation in this class, right? So almost all Taylors we do can be done in 1D. There was one case when we needed 2D Taylor only. And that was when we were studying the F for the Runge-Kutta methods. And let me show you why. Because then we had this f that was, because f is really, so if you think about it, we have a function y of t. That's just one-dimensional. Everything is one-dimensional. You take the derivative, and that is equal to some function f of t and y of t. All right? So if you want to, many times we consider f, all good? Sometimes we consider f a function of time. We often do that, right? And it's fine. F is certainly a function of time. We can put a prime there. That would be df, total derivative of f with respect to time. And in fact, if you want to write it in terms of these guys, it becomes a df dt plus a df dy times y prime, right? Inner product. So we have those issues. But anyway, this is what we're doing. But if you really look at this form of f, it's a function of two variables. So now it became a two-dimensional function, so to speak, right? It's a function of time and y. And the reason I'm a little hesitant to even focusing I don't want to focus too much on the two-dimensional Taylor. Although I think, and one reason is that the time is not that important. So you could have done that whole thing they did in chapter 5.4, just saying, let's pretend time is not there right now. But and you had a homework problem on this that was much more difficult in that chapter, where you kind of had to expand things and find some order of some scheme. One of the later problems in 5.4, I think. And I think I mentioned to many people that you could actually just look at f of y of t and ignore it. But let's just see what they did, because I think they did it. It was a kind of a pedagogical thing to not assume anything. And they just said, first of all, what is Taylor in two variables? This is math 53 stuff. I don't expect you to know much, except that it's kind of obvious how it extends. So, you know, if you have two variables, of course, the Taylor polynomial is a constant plus a delta in one direction times the partial derivative plus a delta in the other direction times the partial derivative. OK? And then hell breaks loose, because there are all these mixed derivatives, and the general form has all these binomial coefficients and stuff, right? But we didn't go that far. We really just wanted the first order term. So don't worry about it too much for this. I'm not going to go further. The rest, we say, is higher order terms in, you see, here's a delta in t square. Here's a delta in the second variable, y square. And here's a mixed square. So everything is kind of ordo second, right? Which is higher order term to us. And the only way we use this is that we then, I think this is the pedagogical part I said. We just said, look, we have our Taylor method. We like them, except that they need f prime. And we don't like computing f prime because it involved all these messy inner derivatives, right? But by the way, I did last lecture that that's also a routine problem. Here's a method. Show me a Taylor method of order 2 or 3. And I did that problem last time. You just have to do the derivatives and bring it all out. Anyway, so the goal of Runge-Kutta was to not do that. And here's the entire assumption. Try to instead move a little bit to the right and a little bit up in this two-dimensional f function, such that this becomes what you want, namely Taylor. And in order to do that, you, of course, had to expand this. So we just used the first order term. So this is going to be the constant plus the delta in the first one, alpha 1 times df dt, plus beta 1 times df dy. And that comes over here. OK? And then they stop and just call it the remainder. Yeah?
So when the question asks for error of order h squared,
Yep.
does that mean you take the Taylor of just before everything, before all bases, or one step?
I think what I'm trying to say here is that in this case, I don't remember your homework problem exactly, but you're right. If you want to go one step further, so in this case, you got away with, let's look what the terms are here. So there is an extra h multiplying this in the method. Remember the Taylor method? They've removed an h, but there is an h multiplying this entire thing. Euler is just h times f, right? So you actually, this becomes h squared. So by just keeping the first order terms, you actually end up getting a second order accurate method. So you would have to, what you're saying is that if you want to go to h3, using this method, you would need the higher order terms, yeah. Then you would need these three terms as well here in order to, using this method, show that. Yeah. But yeah, I think, as I said, I think that's unnecessary. I think you might have had a homework problem where you could have done that, but I would say that if you just show it true for y, that would be fine, and then everything becomes usual one-dimensional Taylor. So I insist again that the goal of this course is certainly not the higher order terms here. But all we did in class was the first line here, namely that a plane. Yeah, I think remember here, this was just one-dimensional, right? And why didn't I need a two-dimensional on this f? I mean, you could. It is an f of a t comma y if you want to. You could actually do this whole framework. But at the end of the line, remember, we replaced all the f's by y prime, and all the f primes by y 2 primes. So this is what I said before. I just treat f as a function of time. And the reason this works is actually because we're consistently evaluating. Whenever we're evaluating, the reason, the times when you can always just do this replacement is whenever I put a time here, I put the same time there. Okay? Now, if you look at how they derived that, they didn't assume that. They just said straight out, suppose you want to find some alpha 1 to the right and some beta 1 up. That's the reason they needed this independent term. In general, if you look at this fi minus 1, what does fi minus 1 mean? Remember, we defined fi to be f evaluated at ti consistently with that one, right? That's it. That's really, as long as you have the consistent t's here, this is just a function of time, and you can take a derivative with respect to time. So in most of our problems, we're doing that. Here, I definitely did it. And then fi minus 1 is really equal to y I minus 1. By the way, just one cautious thing about these notations. When you talk about the method, of course, the thing you're plugging into f is w. Okay? When you talk about truncation error, remember, truncation error is the scheme replacing w's by y's. So what I wrote here is true. This is what we do when we derive the local truncation error. But of course, up here, it's a w instead, right? But that's usually understood from the whatever solution you're working with. And I mean, normally in a computer code, there is no y. There's only a w. You're computing a w. When you analyze things, it becomes you look at the true solution. But that's just notation. Yeah, in principle, if you want a really annoying problem, you could go at this method with all these second order, but you shouldn't do that. Even if you make the assumption of skipping the t, showing fourth order convergence here is quite difficult. But it can be done. I'm just saying it's not a coincidence that we skipped this. But hopefully you got the flavor from the lower order methods, and you know how to do your Taylor, and the rest could be done with the computer. But of course, you want to go higher methods like this. All right? Good. More questions? I like these type of questions. If you don't, I'll just mention some things about this. Operation count, I think, is new. So as I said, Gaussian elimination you know. And if you don't, make sure you know it. The big thing here in chapter 6.1, that was new was operation count. Don't struggle too much about the lower order. Usually it's a question of the highest order terms. But just to give you a little bit of a flavor of what the issues are, some just warm-up problems to just make you think about this would be, what is the operation count? You can think about various things from linear algebra and what the operation count would be. Okay? So a very common operation is a dot product, right? And I think we mentioned this before. What is the operation count? Well, it's equal, if you want to think about it, it's x1 square plus x2 square, etc., right? And let's say we have n numbers. So there it's clear that you're going to have to do n multiplications, right? And strictly speaking, n minus 1 additions, although that's not how you do dot product in a computer. You start by 0, and then you're adding in things. So it's actually n additions as well. So that's why I'm saying that those lower order terms are, they can be discussed. But I would say basically, n multiplications and n additions. Right? So that's easy. Let's look at, how about this one? Where a is m by n. Well, again, you might have to just write it down, but it's compared to the for loop that we're going to do next. This is easy, right? But it still has to be done. And you'll convince yourself that there's going to be m times n multiplication and the same number of additions. After a while, you start realizing that in linear algebra, almost every time operation you do has this dot product flavor, namely that you're multiplying two things and adding them to something, right? So what people usually do is combining multiplications and additions. Yeah? Well, if it's super strictly defined, it doesn't, right? But in this case, it's not. It's unclear what I mean by this. I would strongly object to someone who said, if someone insists that this is n minus 1 additions, I would object to that. I would say that depends on how you do it. The computer doesn't do it that way, because you don't want a special case for just one element. But of course, strictly speaking, if you have one element, there's going to be one multiplication, and it looks like, why would you add anything, right? But no, a good computer code would add one. So in that case, I wouldn't. And that's what I talked about when they do their derivations as well. These ones can certainly be discussed. Although if I said exactly how to do it, and by the way, one way to tell you exactly how to do it is to give you a computer code. This is unclear what I mean. If I wrote the computer code, let's do this in computer code. Let me give you two variants here. Dot equals, this is how I would do it. And in MATLAB, you never do 0.0, but when you start coding in things like C, you better get used to doing things like that. Then you would loop from 1 to n, and you would add in dot equals dot plus something, right? Namely, x of I squared. So if I tell you this, it's exactly what I wrote up there. Okay? The alternative I was talking about is to not do this, to try to save one addition, right? But you can all see that that actually leads to a special case. But you could actually do it in the following way, which is OK. You could do dot. Well, here's a great warning if you want to think about robust and software design. How about, what do you think is wrong with this code? And same thing as over there. So I'm setting the dot product to the first one square. This is how you would do it in your head. Dot product, you take the first one square, and then you start on the second, and you go to the end, and you add in the squares. Sounds great, right? I saved myself one addition. And this code, of course, you would have to subtract 1 from here. And not part of the course, just if you're interested, computer scientists, what's bad about this code?
You assume it's 2.
What?
You assume you can start at 2? Or
Yeah. What's bad about that?
it might be only one element.
That's not a problem. If you're saying that if there's only one element, this would be a problem. What would MATLAB do if you do for I equals 2 colon 1?
Aren't you accessing elements when you do that?
I might, but a for loop from 2 to 1 is well defined in MATLAB, and it doesn't do anything. So that's fine. One element is fine. In fact, it will just do this thing here. What's bad? Yeah. Yes, 0 elements. And that's the case that nobody thinks of, but it will happen eventually if you write the code. This code will do the right thing if you give it 0 elements. That one will not. That's not that much part of the code. I'm just going to point out that it depends a little bit on the detail. A code, however, is extremely well defined. It's hard to argue with operation counts with a code. Anyway, this was a matrix vector product, right? Matrix product, I think we talked about that last time. But let me go straight out of for loop. No, I want to show, no, let me do the matrix because I had a little comment to make. How about AB? Where A is m by k, B is k by n. All right? And you might actually want to, I don't know what you want to do. You might want to, why not, I mean, you can use computer code or math language. In math language, we defined a matrix product, element ik, to be a dot product, remember? 1, 2, no, k was already used. You need something going from 1 to k, and you need to take a rho I. It's so easy to use MATLAB notation sometimes. People actually do that a lot. But we can use the math notation of I, L, B, L, J, right? So if you want to, you can write your matrix product like this. And what you have to realize, that each number ij you want to compute is going to need, it's just a dot product, right? It's going to need k multiplications and additions. But how many of these do you have? I guess you need to know the dimensions of A times B, which is m by n. So regardless of how you do this, this gives m mkn multiplications and mkn additions. Right? Of course, the computer code does, I think, make this easier by saying for I equals 1 to m. Already there, we're telling you what the dimensions are of the, for j equals 1 to n, for L equals 1 to k. And then you do a multiplication and an addition. And I don't care what you do because I'm just counting operations, right? So if I wrote this, it's pretty straightforward like that. Now, what was the difficulty with the Gaussian elimination? That kind of looked like this, right? The only difficulty, I mean, it was a little longer. There was a special case. You computed multipliers and stuff, right? But overall, the big difficulty with that was that it was not 1 to m, 1 to n, 1 to k. I mean, this for loop is obviously just m times n times k, right? The problem there was that I snuck in i's and I plus 1s and stuff here, okay? That's when you had to do a little bit more calculation. And I have an example of that. First, just a quick little comment. How about a, b, x, where x is, I guess, n by 1. What's the operation count for that? This would be a trick question. But in order to make it a question, I think, in order to make it a trick question, I think I would have to ask, what is the best possible operation count for that? You see where I'm going here? We talked about, we actually proved that matrix multiplication is associative in the sense that you can choose what order. It's not it doesn't commute, but you can choose which order you're doing. Okay? Which means that especially if I first ask you to do this, I'm sure the trick I wanted you to fall in would be to say, well, we already did this, right? And that was mkn. And then the next one is really one of these guys. And you just add them up and you're done. Is that the best possible thing you can do? Bx first is just super much better. I mean, this is insane to create that matrix. Because Bx is a matrix vector product, which really just scales like a square, right? Imagine, just for rough, the dimensions of m and n might matter. In fact, if this k is 1, the argument is not that important any longer. But that's kind of boring. But anyway, in some cases, it doesn't matter that much. But you definitely want to do this first. Anyway, let me do a for loop with i's in it. So I don't know if this is a method, but I just made it up. So suppose I do 1 to n. This is easy, actually. J 1 to n and k 1 to j. Okay? So I did almost exactly the same thing. No m and k, just n's. But this guy has this difficulty that it's just going up to j. And the first thing you realize is that in the Gaussian elimination, it was often starting at j and going to n. And that's just annoying, but you can figure out how to do it, right? It becomes my n minus j instead of plus 1 or something. And then you do something here. What's the operation count? Actually quite easy compared to the ones, because I think in Gaussian elimination, not only did we have the extra difficulty that it went from j to n, but we also had it there. In this case, it's actually very easy, but you can write it down and say there's a sum from 1 to n. You might want to be smart and realize that this I doesn't even show up anywhere. So this sum, you should very quickly replace by just n, just like we did over there, right? But the j does show up, so let's write it. And if we're not too clever here, we just write everything. 1 to j, right? And then we're doing, what do I put here? If I'm doing one multiplication here? 1, right? So if you write all these loops, of course, then you put a 1 there. Maybe I would do 2 multiplications just to trick you. Then you put a 2. But in most cases, we saw it was a 1. OK, so what is this? Well, I mean, this is easy, right? That's just j. And I already mentioned that that's just an n. So you should pretty soon just simplify this to an n from that guy. The sum we don't know how to do yet. But this is, of course, just j. Adding up j once is j. Right? But then eventually you'll have to use those formulas in order to get it down to something like, in this case, I think it's something like that. Half, right? So it's similar to what we did, just a little different numbers. And if I did put the Gaussian elimination thing, suppose I put a j there, then you can see that actually the Gaussian elimination thing put an I there and there. Then we ended up getting j squares here, but there was a formula for that. That's, yeah. Often, if we ask for the leading order term, the answer here would be n cube halves. N cube is really the main thing, realizing that it's cubic. That's pretty easy to get at. But the fact that it's cubic divided by 2 is also important. The fact that you have plus n square half, I did not make a big deal out of it, okay? Because that's, you could do that, but why? We're too busy to worry about those lower order terms. N is supposed to be big. All right? Now you know how to do any operation count, right? Partial pivoting. If I ask you do Gaussian elimination, of course you know how to do it. But if I wanted to add a new difficulty, I would force you to do row swap, even if you don't need to, right? Because I did emphasize that in numerical analysis, you do what's called partial pivoting. So if I say, do Gaussian elimination with partial pivoting on this matrix, that means this algorithm, which is really just Gaussian algorithm, but you always make sure that the thing you're trying to use for elimination, the pivot element, so you come this far, right? You have all zeros here. And you're about to start putting zeros below here. Well, every time, at every step, you've got to first make sure that the largest element, maybe this guy, is swapped up to that point, right? Just like you would if it was 0. So I'm saying you already know how to flip rows. You've done it in Math 54. But here we do it, even if this is a 1 and that's a 10, you've got to do it. You've got to flip. Okay? That's the main math. And it seems like a detail. It's kind of really important, but of course it seems like a detail, but it has to be done. Just review of linear algebra. We did go through all this. LU is a little bit new to some of you. I know it was probably shown, but it's important to see. It's really just a way to write your Gaussian elimination. You might want to remember the rules. U is what you get when you're done. L has all these multipliers, and you might want to think about the sign there. If I have a little example, we can just talk about the sign. But it's really, this is based on the fact that you subtract the pivot row. If you don't get that right, you will get a sign error there. Of course, you can always multiply these together and check. What about the P? Well, if you do row exchanges, of course, this is not true. And it turns out you can put the entire P to the left of the A, or take the inverse and put it on the right. So this is quite common. I think Strain had a question in his exam that I posted saying, find the PA equals LU factorization of this matrix. And that could be a little difficult problem if you have to row swap. But it's doable in the sense that every time you swap a row, it goes into this P. And you can see that it ends up being just like A equals LU, but every time you swap a row, you've got to flip the P. So you get, what would an example be? An example would be that suppose you have 1 there and a 10 there and anything else, right? Your first step would be to flip those rows and put the 10 there and the 1 there. Okay? As you do that, you keep track of a P where you also, what is P if I don't do any row swaps? Identity, right? So I think that in Strain's example, I think that it was an easy problem. He just wanted to test that, right? But P doesn't have to permute anything. Ideally, it would be great if you didn't have to. If you have to permute, you just permute the identity matrix. Don't it look like that? And then you keep on going, and you're done. If I have to flip more, you keep on flipping. But that's what these permutations do. I have an example, but it's actually a symmetric matrix. So let's just look a little bit at 6.5. I guess this material is a little bit more new, although you do know what a positive definite matrix is. Yeah? You do them forward, because P is defined to be on the left side. Remember, if you want to put P on the right side, it's the P inverse, right? And the way you're thinking, I know it means that that's really the backward one, right? But we actually define this P to be multiplying A, which means that everything you do to the matrix A in a forward sense has to be done to P in the forward sense. So if you flip row 1 and 2, you flip them here. If I later on flip 2 and 3, then you flip these two. You can, of course, always check this. Small cases like this, if you have a few minutes left, final exams are hopefully not as stressful as midterms. Multiplying together these things to make sure you got it right is not too much work, I think. All right, a few things here. Actually, the big focus here was actually not diagonally dominant. It was positive definite. And that's the important property. But just diagonally dominant, it doesn't hurt to know that if your diagonal elements of a matrix are greater than, in this case, strictly greater than or equal to the sum of everything else on that row, you have a lot of nice, that's a great matrix. If you see such a matrix, you're usually happy when you do linear algebra or numerics or whatever. First of all, you know that it's non-singular. You don't have to worry about row interchanges. It will never happen. And it just works fine. Okay? So that could be a quick way to check that something is, you don't have to compute determinants or anything. You know that it's non-singular. Of course, the extreme case here is a diagonal matrix, where, of course, a diagonal matrix with non-zero, with positive diagonals, right? That's obviously a strictly diagonally dominant matrix, because everything else is 0. And that's indeed an invertible matrix. But this was the more important topic, because these matrices are all the time, they show up all over the place in any type of engineering and science. Positive definite matrix, symmetric. Why don't we just call them SPD, symmetric positive definite? These matrices are symmetric. I mentioned that there are textbooks that talk about matrices with this property that are not symmetric. Don't go there. It's easy. It's symmetric and this. If I give you a matrix that is not symmetric and ask you, is this, if I give you anything and ask you if it's positive definite, the first thing you do is realize that it has to be symmetric, right? So if I give you this, you immediately say, no, it's not positive definite because it's not symmetric, right? Now, if it is symmetric, then how do you determine if it's positive definite? Or not? What? So we have a number of ways, and we'll look at them, right? Some of these ways could quickly be used to exclude something. For example, is that positive definite? No, because that's property number B there, right? Okay? Now, that doesn't mean that this means that it is positive definite. It's only implication in the forward direction there, right? So here you have to do more work. Maybe if I give you a super big matrix with this little thing here, suppose I have, this is a 1,000 by 1,000, it's a huge matrix, and I give you those 4 numbers. Is it positive definite? Based on which property? I think I'm thinking of, oh. Yeah, well, there are various issues there. I'm thinking of D. If you take this little subdeterminant here, which is basically the product of these, it has to be less than the product of that, and it's not. So then immediately you can say it's not. But no, in general, you don't get away this easy. In general, it's really hard to show that something is positive definite. And let's see what else we have. So this was the other thing. You could actually do all those determinants. Okay? So you could, in fact, this would immediately lead to what I just said, because you would say, this is a determinant, it's 2. The next principal leading principal submatrix would be this 2 by 2, and its determinant is 2 minus 9, which is negative and is not positive definite, right? However, I said we don't like determinants. Really, the way you figure this out is Gaussian elimination. Unless you could do a shortcut, this is how you figure it out. And the story is pretty, the corollary here says it best. A matrix A is positive definite exactly when you can write it as LDLT with the usual L, but D has positive entries. Okay? The way you do that, someone mentioned yesterday something very clever in office hours where you can actually just put in some numbers and simplify things and calculate this. And I said, that's amazing, but it's not how you're supposed to do it. If I ask you to find LDLT, it's understood from the examples we did that you first do LU. Okay? And by the way, if I ask you to do LDLT and I give you non-symmetric, I mean, just look at the matrix, right? If it's non-symmetric, it cannot be done. LDLT is a symmetric matrix. How do you show that? How do you show that something is symmetric? you take the transpose, right? Symmetric means A transpose equal A. So if I tell you that this is prove that this is a symmetric matrix, what you do is that you take its transpose and you realize it's L transpose, transpose, D transpose, L transpose, right? And you're not quite done, but transpose twice gets you back to where you started. Diagonal matrix transpose, what is that? That's a do nothing, right? So that's how you show that that's a symmetric. So it only works if it's symmetric. Anyway, here's a little trivial example. Find LDLT of this guy. I actually came up with these numbers by choosing L and D and multiply, because I want easy numbers. Maybe a little too easy. Anyway, you don't know those numbers, so you have to do it anyway. And this is also a good time to talk about what those multipliers are supposed to be. I know probably, when you do this on your own, you're thinking, let's add 3 times that row to this row. And that's indeed what you're going to do. But the multiplier is not 3. It's minus 3, because they're defined as subtracting. OK, so that's maybe a slight source of confusion. But anyway, this is, you don't touch this row. By the way, am I doing partial pivoting? Did I just do partial pivoting? I did not. If I did, I would have to move this guy up there. Its largest in magnitude guy has to be the pivot element. So this was not done by that. But that's OK, because it's positive definite, so it's going to work out anyway. So we added 3 of that, right? So that gave us that, and then numbers are super easy here. It's a 1 and a 4. Here, again, we're adding 1 times that, but the multiplier is minus 1. So while you do this, you might want to build your L. You don't have to, but you could forget all these multipliers. But really the way to do it, the way a computer would do this, is that you have your L here. You know that it's going to be 1, 1, 1. And you just put your multipliers here, right? So when you subtract by 3 times the first row, you put that there. When you subtract by 1 times the first row, you put that there. So you get 0, and there we get a 4 and a 17. All right, and then one more step gives us the matrix we want. Minus 3, 0, 1, 4. And this multiplier is plus 4, right? Because I have to subtract. That's just how it's defined. So this is 4. And then I get a 0 there and a 1 down there. OK? All right, so we have our L. This is L. You would say you're almost done here. If I asked for LU, you would certainly be done, because this is U, right? If I ask for LDLT, that is the L. You just need to find D. And we've said it in many ways, but one way is that it's the diagonal elements of U. So you can almost immediately just now say D is 3, 1, 1. And then you're done. If you want to check your calculations, what has to be true if you pull out 3, 1, 1 here? What does this become then? L transpose, right? And it will, if you did it right and if it's symmetric. And that can be shown, otherwise it wouldn't work out. But so you can do it for checking. Strictly speaking, you don't really need this matrix except for the diagonal entries, because it was symmetric. And in fact, you know what a computer code would do. It would save a factor of 2 by doing this right. So a good method for this would be twice as fast as the general case. Anyway, let's do the L twiddle too. So we're done, right? And this meant that this means that A is equal to L DLT. And the best way to find it was to first do LU, right? And now what if I want L twiddle transpose? What if this was a minus 3? Then you would have to tell me that. What about L twiddle? So let's do the L twiddle for this case. Basically, you just take the square root of D. I mean, you can remember this in a shorthand, but the way you think about it is to say, write this as L square root of D, square root of D, L transpose. OK? And then this thing here, you call L twiddle. And then you can convince yourself by the same as before that this is L twiddle transpose. But to get the matrix out, of course, you would say L twiddle equals, L times D. So what does it mean to multiply by a diagonal from the right? From the left was scaling rows, right? But from the right is scaling columns. So you would have to take this L and scale the columns by square root of 3. It's a little annoying, but I guess we could do it like this. Square root of 3 minus 3 square root of 3 minus square root of 3. Square root of these are 1, so this is just 0, 1, 4, 1. In this case, you really probably want to multiply it with this transpose to make sure you didn't mess anything up. But that's the whole procedure. And now let's go back to what I said before. What if you got a minus 3 out here? I mean, you could go compass, but you probably don't want to do that. I would probably say that the L twiddle doesn't really exist. In fact, this L twiddle, it's not called twiddle in here. I call it L twiddle to not collide with our L. But here it says that the L twiddle here they think should have non-zero diagonal entries. So that excludes the complex case as well. All right, and this we asked about. I'm not saying I won't show you tridiagonal matrix just because they are fun, but we didn't say much about these guys. That's just matrices with special properties. All right, more questions on 6. Does this cover everything? I'll erase here in the meantime. All right, so well, just interrupt me with any question at any time. I looked through everything, and clearly I can't review. I just randomly went to chapter 4 and thought of a problem that I think some of you would find difficult. Let me just show you what I was thinking. Where is chapter 4? So remember the very first one here is 4.1, right? And then the rest of the chapter was integration. So you might easily forget the differentiation. So let's just look at that. It seems like such a straightforward thing to do, but it's really just the same pattern. It's just easier, I guess. So it's got one section, while integration got 4.2 all the way to 4.9. You know, it's a little disproportionate. Differentiation is based on various things, but the general way we did it was the following way. Differentiation of Lagrange polynomials, right? So you'll probably memorize some of these guys, especially the central difference, the second row here, you certainly know. And the 1 minus 2, 1 formula for the second derivative, you all know. These are a little trickier, but they can be derived in various ways, and you could do all types of things, right? But this is kind of what we did. I'm just saying, going back to basics here and asking for something like this. Find a finite difference formula for f prime, the derivative of f at 0, in terms of f minus 2, f0, and f at 1. All right? So is it clear what I mean? Finite difference formula means that you are going to multiply these numbers by something to estimate an approximation of f prime at 0. Okay? Does it fit anything? Can you use this slide? Why can you not use formula 2? Plugging in x0 equals 0 and h equals what? Well, that's the issue, right? That's a central formula. That's an equidistant formula. It goes one step to h to the right and one step to the left and subtract them. If I replace this by minus 1, you would be dumb. You would say f1 minus f minus 1 divided by 2h. But I'm tricking you, and I'm giving you another point, which means that it's back to basics. So basically, I'm giving you 3 points. There is a function that has to be smooth, or Taylor doesn't work. And I'm telling you that number. I'm telling you that number. I'm not telling you that number. I'm telling you that number. You see that this is what I'm doing? And I'm asking you to estimate this slope. Seems like a reasonable thing to do. Actually not, because then it would be a routine. But you know, you might want to do this. But the only reason I do it is to make sure that you don't just do the formula, but see how to do it. So what's the procedure? It's kind of the same we did for all the integration things. Just fit a polynomial and differentiate it, right? That's how we derived Simpson and trapezoid and all those Newton codes and everything, fit a polynomial and integrate it. Now we fit a polynomial and we differentiate it. And that's what this slide is saying. But you might not need this slide if you just remember that. So the solution to this would be, first you find the interpolating polynomial. Remember I said that you already know how to fit the quadratic to 3 points. But it would probably be based on solving a 3 by 3. Kind of annoying when you have these values. This is where the Lagrange form really makes it easier, because it's going to be some polynomial multiplying each of these, and that's a great form. So Lagrange form might sometimes not be the first thing you go at for fitting polynomials, but for these it really is. So I would say you just go, and you'll see, I think you'll appreciate it after a while. So the Lagrange form, you have 3 points. You should know these things. You're standing at -2, and you're doing x minus all the other guys multiplied together. So it's going to be x minus 0 times x minus 1. Right? Then you're dividing by the same thing, replacing x by where you're currently standing, namely -2. And although it seems a little nasty, but it's really so easy and straightforward too. This is multiplying. What is this? This is what we call L of degree 2, comma 0, remember? And often we skip that n and we just call it L0. And this is that unique polynomial of degree 2 that is equal to 1 at this point and 0 at the other ones, right? At 0 at these two. Okay? So by multiplying this by f of -2, we're getting a polynomial that goes through this point, but is equal to 0 at the other two, right? That's what I've done so far. The key with Lagrange form is to now do the same for these guys and that one, and add them up. And if you think about it, clearly, since this guy is 0 there, it's going to be that polynomial. Okay, so let me keep on going. Plus, the next one will be, so again, this is routine. Now you're standing at 0, and you're going to do x minus the other one. So it's x plus 2, x minus 1. Replacing x by 0, you're getting this, right? And this is multiplying f of 0. And then finally, you're standing at 1, and you're doing x. You're doing the other ones. And then you're replacing it by yourself, 1 minus 0. And that's multiplying f of 1. Okay? So that's just write down Lagrange. Okay? Now, it looks nasty, but everything in the numerator are just numbers, right? It's a polynomial. It's not that difficult. So the first simplification is probably to just write it as something like did I even simplify it? Yeah. I guess we're getting 1/6 coming out of this. And then it's just really x minus 1 over 6, f minus 2. Then we have a x plus 2, x minus 1. And this here becomes a minus 2. So I can put a minus there, divided by 2, f0. And the last one is also just an x plus 2. And there we're dividing by 2. No, 3. All right, fine. Anyway, this is the answer to what is the polynomial. This is the polynomial interpolating these 3 points, right? But the question was, find a formula for estimating the derivative. Well, it could be anywhere, but in this case, we're asking for the derivative at 0. And in order to do that, you have to differentiate. Differentiate. So then you're getting the derivative of this polynomial, which is routine, even easier. But you have to do it, f of minus 2. And you see, you appreciate the Lagrange form that everything is just multiplying these guys, which is what we want at the end. So it's going to be quite easy when everything is said and done. This was divided by 2, f of 0. And the last one was this. All right. This is a straight line, right? But it's written nicely in terms of the unknowns, f's. So that this gives the final formula. You want to estimate this, right? It's not going to be exact, but it's approximated by the derivative of this polynomial at 0, which is equal to just setting things to 0 here. So you're getting these numbers coming out of it, minus 1/6, f of minus 2. Here we're getting a minus 1/2, f of 0, you're getting a plus 2/3 f of 1. And this is it. This is the answer. It would be probably more interesting to, instead of minus 2 and 1, make it minus 2h and plus h. I just kept it simple, because usually we want this in terms of that. Can you look at it and just quickly convince yourself that you didn't make too big errors? What would you do to just look at this and see if it's reasonable? What do we do with the quadrature formulas? We look at simple functions, and simple functions are actually the order of, you could have various simple functions, but polynomials are usually the way. What if I try to find the derivative of a constant? Well, clearly, I would get minus a sixth minus a half, which is minus 2/3, plus 2/3 equals 0. So it does differentiate a constant correctly. That seems like a good thing of a scheme, right? And you can try the linear one and the quadratic one and see that it would do those as well. So that's probably what you would do, a problem like this. Anyway, I just thought that could be fun to do. Of course, if those numbers would fit any of these things, many people ask memorization. I do not like memorization. I hope you feel that the midterm, I gave you the formulas that were a little iffy, and I don't want you to memorize. But of course, if I ask you to do that with a -1 and you remember the central formula, you could just write it down and say, look, this is the famous central formula, and it has this order, and we're done. Unless I ask you to show it. All right, we had all these other integration things. I did, though, promise to quickly just say a few words about all the MATLAB functions. And it's actually not all of them. So let me just look at the ones let me just go through these. This is not covered. That was a utility that we used, remember, in 1.3 to just look at floating point numbers. This you worked with yourself so much. So review your programming assignment 1. If you do that, you don't need to review my bisection table. This was the basis. This, together with Newton, was the basis for your programming assignment 1. OK? By the way, we're posting the solutions. I will post it to the last one as well. That's a great preparation as well, to just see how it can be written in other ways and see that. Fixed point is, of course, a function you wouldn't even write, because it's a 1. Oh, did I lose that? OK, whatever. Let me start MATLAB. It was just a one-liner, right? But there was a while loop around it and a termination criterion. But the Newton, of course, you've done so many times by now. How many times have you done Newton? You did it in program assignment 1, and you did it in 2 to solve for that root of the spline, remember? And now you did it again in program assignment 4. You see the focus on Newton here? We're solving equations. These, Stephenson, you know the method. I think you could be able to implement these methods on your own easily. And Horner is the same thing. It's a routine problem to do by hand by what you would implement it. Many asked, do we need to know Müller? And I said, whoa, all these numbers here, they were kind of complicated. They're fitting this quadratic. What you need to know back then was, remember, Müller's method fits, instead of Newton fitting a straight line, or not, sorry, Newton, instead of a secant method fitting a straight line and finding that intersection, this just takes it up a dimension and fits a quadratic. And that you remember. You don't remember all these formulas. Neville, well, I still don't have internet, but Neville we didn't focus on too much. This is also a routine problem that you would probably learn just the math formula. I wouldn't go to the computer code on this one. You know how much I like divided differences. I emphasized it a lot. I put it on the midterm, or I didn't. In fact, you could do whatever you want on the midterm. But I think problem number 2, where I asked you to fit 2 polynomials to pretty simple data, got extremely simple by the divided differences method. Okay? I'm just saying you can fit polynomials in whatever way you like. Why didn't I use divided differences for this? This was fitting a polynomial. I kind of could. It's just that it's not that bad. But that table gets a little messed up when it's not numbers. It's not numbers, right? It's unknowns. So in this case, it was convenient with a Lagrange form, because it's really some polynomial multiplying these numbers. But no, in principle, if I told you this was 3, 1, and 2, my preferred method of fitting a polynomial is divided difference. I think that's very convenient for hand calculation. In particular, if I make it a Hermite, like I think I did on the midterm exam. The splines, even more so. You can read these functions, but I don't recommend even this strategy. This is implementing, remember these codes? Did you even look at these codes? You certainly used them for program assignment 2. So you should really review how you use them. But these expressions are just all those matrices showing up in the slides. And you can see from all the old exams and anything we do, your homework, for example, that when we ask the spline problem, we will probably simplify it a lot. Typical thing you'll see from the old exams, I actually did prepare one, but it's not a big deal, is that we give you, for example, here's a spline, and we give you a lot of the coefficients. So the simplest I could do, if I just make it one interval, it's not really a spline. It's just a polynomial, right? So let's make 2 intervals. I think I did that on the blackboard. In general, that creates an 8x8 system to solve, and we actually did that on the blackboard. But that's insane. So I would simplify by, in this example, I would give you the left one, and I would give you 2 of the coefficients in the right one, or 3 or 1 or something, right? And then it would just be no linear system to solve. Because what you want to check is just what is a spline and how does it work? And you know what it is. It's just all these conditions up to second derivatives on all the interior points. And that's what splines are. So those codes are not that important. And this we used for the programming assignment. Richardson is a procedure you're often asked to do. You were asked to do it actually on the midterm. Okay? And again, you want to remember the math or the homework, you did routine things. The computer code could add some insight. I'm not sure how much. What is Romberg? It's Richardson applied to trapezoidal method. Okay? Kind of a neat code. But again, if you're asked this on a final exam, you would probably just have to compute those trapezoidal rules and start doing Richardson by hand. So, that's probably not that important. Gaussian quadrature, you remember it, right? I mean, a typical question on the midterm, I gave you the points. That was not even the hard point. If I give you find A, B, C, D to maximize the degree of precision of this quadrature formula, that is a routine problem, right? It's kind of like here. Find the numbers, -1/6, etc., that find this derivative. But instead of differentiation, it's integration, right? And you can actually do what we do, fit the polynomial. But in those cases, it's usually easier to just try 1, try x squared, right? And go as far as you can. That's usually how we do that. This computer code is just complicating things. I might squeeze in a double one, but it's going to be, you know that we never did 2 fancy double integrals. But you should know that if you do Simpsons on an interval, and I ask you to do it on a square or a rectangle, it becomes this outer product, right? So if it was 1, 4, 2, 4, 1, now it becomes 1, 4, 2, 1, 4, 1, and the same there, and the multiplication of all of those, right? That's certainly a fair game, because we did those in homework. In fact, in the homework, you did even things where it was scaled in weird ways. But then I asked you to use my code, I think. Did I? Simpson double, yeah. So, that's a little out of the bounds of what we do. So don't worry too much about that. This was used for the homework. RK4 we used so much. You should be able to write your own RK4 in math. It's just super simple and super short. I mean, this is on the border of what I think is memorization to remember these numbers. The numbers are 0, a half, 1, and then combined. But I don't like memorization, but just the idea of writing these up is fundamental. We use this code so much, it's really, really important. Okay? So RK4, no matter how you remember it, it's a good thing. This one was, of course, a mess to Runge-Kutta-Feldberg, right? Because there are all these coefficients. So many of you freaked out when you saw this. Those numbers are not important. What's important is the idea that there are 2 methods. One is more accurate than the other. And by just subtracting them, in this case, you don't even see the subtraction, but there was a way to figure out this estimation is done here, actually, of the error, right? So local truncation, this is the adaptive. This is 5.5, I think. A little demo of the stability. Gauss elimination, I also think is very important. We wrote this code from scratch, remember? Just review that you know how to do this. Writing these for loops, maybe not the pivoting, but the idea of nesting these loops. I know it's tricky with the eyes, but this is really the shortest and most definite way to describe Gaussian elimination. And back substitution comes further down. And demo there was not, that already. All right, that was a super quick, but I know so many of you asked, we know to know Miller.m, and I wanted to just give some feedback on it. Come to office hours today, now, or next week, and that's it.